Variational autoencoders. See these faces below. So, do they look real, right? What if I tell you that none of these people actually exist? I'll let you have your moment. What you see are results from a generative deep learning model. That's right, a computer made this. These are the models which are the culprits for those fake videos you see of Obama and Trump. However, generative models are also used for really cool applications such as creating music, recoloring black and white photographs, creating art, and even in drug discovery. There are many models that fall under the category of generative models, and the popular two are generative adversarial network and variational autoencoders. So where there is a will, there is a variational autoencoder. So these variational autoencoders are a popular and older type of generative models that are based off the structure of standard autoencoders. It consists of encoder, decoder, and a loss function. So these variational autoencoders let us understand the latent representation of an input. So using them, we are able to represent and even synthesize complex in the context of simple models. So these variational autoencoders have already shown promise in generating many types of complex data sets such as handwritten digits, faces, and synthesizing new molecules. So let's understand what is autoencoder before diving deep into this variational autoencoder. So an autoencoder is a neural network that learns to copy its input to the output, and that are supervised or unsupervised learning techniques. Unsupervised learning techniques means the network only receives the input, not this input label. So this autoencoder has an encoder, a latent space, and a decoder. Now this encoder network will compress the input and decoder will decompress it to produce an output. This encoder network is composed of convolutional layers. So if you're familiar with this convolutional neural network, you would know that it compresses the input with convolutions and pooling layers to create a much more compact and dense representation of the input. This is then used by the fully connected layers to make a prediction. So this encoder network works the same way and outputs a dense representation of this inputs called encodings. And the decoder network uses deconvolutional layers, so which is pretty much the reverse of convolutional layers. Oh no, what a big loss. You must be thinking, right? Like, so when this data is compressed, there must be information lost, which means that information can't be recovered in the decoding process. This is called a lossy encoding. If it doesn't lose any information, then it is called lossless encoding. The encoder learns to reduce this data to only that important information, and the decoder learns to take that compressed data and decode it to get the final output. An autoencoder's goal is to make its output similar to that of input. So by training it on a library of samples and adjusting the model parameters, it is able to produce samples that are similar to the input. Sounds easy, right? The hard part is compressing all that information through this bottleneck. So imagine trying to stuff a pillow into a purse. So when you are trying to stuff that pillow in a purse, you will have to press and squeeze in it. So depending on how big the purse, the less you will have to squeeze and press the pillow. Thus the shape of this pillow won't change much. The same way, the more variables the bottleneck has to represent the information, the closer the output will be similar to the input. So because of its ability to encode and decode data efficiently, autoencoders are great and perfect for dimensionality reduction, data denoising, watermark removal, feature variation, and image segmentation. So what's the problem with the standard encoder? So though autoencoders have many applications, it can still be limiting. Like autoencoders are only able to generate that compact representation of this input and reconstruct the input, which is great for data denoising and dimensionality reduction, but not for generation. So when we generate new images, we don't have to replicate the image. Instead, we want to generate variations of this input. This is because the latent space where this compressed inputs or encodings lie is not continuous and cannot be easily interpolated. So this latent space for an autoencoder groups the encodings into discrete clusters, and this makes sense as it makes it easier for a decoder to decode. So to illustrate this point, let's say we have had a box, and in this we have three distinct piles of candies: candy can, lollipops and jelly beans. So these piles of candies, they represent the cluster of encodings in the latent space. Now you are told to choose the candy you like blindfolded. So you can't see where the candy groups are, and also the groups are small. So there is a higher chance of you not getting anything than actually getting a candy or candy. Yeah, similarly, it is hard to generate new data because there are huge gaps between the distinct groups. So this means that every input has a vector in the space, but every vector in the space does not have an input. Remember, it means that every input has a vector in the space, but every vector in the space does not have any input. So the decoder has no idea on what to do. During training, it has never seen encoded vectors from those gaps. So even though it will create an output for every vector, most of them are not recognizable, right? Next is variational autoencoders. They are great for generating this completely new data, just like the space we saw in the beginning. It's able to do so because of its fundamental changes in an architecture like encoder, latent distribution, which means mean vectors, standard deviation vectors, and a sample latent representation, and the decoder. So where comes the difference? So the primary difference between this autoencoder and this variational autoencoder is that autoencoder will cluster the encodings into distinct groups, whereas this variational autoencoder encoding clusters are not distinct and are not continuous. So they are mapped to the distribution, making it much easier when sampling from this latent space and generating new images. It is able to do so because the encoder is outputting two vectors, a mean vector and a standard deviation vector. So by using the two vector outputs, the variational autoencoder is able to sample across a continuous space based on what it has learned from this input data. So intuitively, the mean is where the encoding should be in the latent space, and the standard deviation is the area around the point. So while training, the decoder only learns that one single point in the latent space, but also from the vectors surrounding the point. So just like a regularization guy, that is only mapping the vectors to the distribution is not enough to generate new data. So since then, there are no limits on what values the mean and standard deviation vectors take. So encoder can return distributions with different means for different classes or clusters with small variance from the mean, so that encodings don't vary much from the same sample. So resulting in encoded distributions being far apart from each other. So this just allows the decoder to recreate the input. Sound familiar, right? So we want it so that all the clusters are continuous and kind of overlap. So to make sure that our variational autoencoder do not become a standard autoencoder, we need a regularization term. So we can introduce the KL divergence to our loss function. So this regularization term will force the encoder to distribute close to a standard normal distribution. So by doing so, it will make sure that distribution are much closer and actually overlap. So this results in some sort of certainty that the encodings are truly continuous. So by only optimizing for the scale divergence, the encoder will randomly plot the points close to the center, and there won't be any cluster, just a mess of points. So we want it to be more organized by the classes, and so we will have to use a reconstruction loss. So these two terms will make up the loss function of this variational autoencoder. And what's the future of this variational autoencoder we talk, especially in healthcare? Sure, generating faces, handwritten or handwritten numbers are exciting, but what excites me the most is generative models being used in healthcare and drug discovery. So in silico medicine, it's a biotech company which has been able to synthesize a new molecule within 21 days and validate it in only 25 compared to 2 to 3 years required by pharmaceutical industries. That's crazy. And this is just the start, and generative models are on the forefront of innovation. So these rapid discoveries will result in wider accessibility to people across the world. So using our genome data, we can have personalized medicines that are much more effective. So imagine if we could synthesize new drugs in the time it takes you to make a hamburger. So possibilities are truly endless. Thank you.